Good morning, everyone. Uh, I'm glad to see all of you back after a nice, restful day yesterday. And we're starting our second part of the workshop. And our first speaker is Professor Andrei Okounkov.
Thank you. So, maybe I'll begin with a few general words. This is a school uh, dedicated to memory of Igor Krichever, and somehow maybe seen a little bit as a continuation of the tradition he was starting. Um, so different speakers of the school, they talk about maybe different parts of their lecture related to different parts of Igor's work. It's my job to talk about his earliest work, which was in topology. So this is following Novikov Sergei Petrovich, who also very recently passed away. Igor did some very important work in topology, which will be the subject of my lectures, and then moved towards integrable system. But for him, I think that already in his topological papers, you see Baker-Archies functions and so forth. I think for him it was always the subjects were always very, very connected, and in fact maybe they foresaw the level of interaction. So right now there's if you look at the forefront of integrable system, there's lots of interaction between questions in topology and into geometry and so forth with integrable system. And this is maybe if you be more clear from Nekrasov's lectures. So this is, but anyhow, this is the subjects are really really interact very strongly. And so maybe this already in the Novikov school, they somehow foresaw this many years ago. And so my goal is to maybe report on just try to explain what's Krichever's elliptic genus and prove rigidity, other properties of this genus, and maybe say a little bit how this generalizes further toward what we do now in the field. As to why would people in integrable system be interested in this? So of course you can. It's of course great if you can apply your knowledge of representation theory, integrable system, and so forth to learn something about geometry. But maybe you will be, for those of you who don't know, maybe you'd be be important to learn that in fact there are many there's there's a ways to argue geometrically about formulas, and especially it's especially nice when you get to argue geometrically about formulas with elliptic functions, because if you have a complicated multivariate expression in theta functions, it's quite difficult to see that this is simplifies anyhow. Maybe it's equal to 0, and the typical kind of argument for proving various elliptic function identities is well, you check that this is an elliptic function, transforms correctly, and you also see the function, it transforms correctly if you shift by periods everywhere. But then if it's a rational expression, you'd like to show that it has no poles. And then traditionally people just do it by, they roll up their sleeves and they just kind of just do it to prove that all poles in some expression cancel. And geometry provides a much more powerful way to prove that something is some rational expression in maybe elliptic function, in fact, is regular. All poles cancel. In multivariate expression, that can be pretty complicated. And there's a geometric way to see that in fact they all cancel. And that's so if you're not interested in geometry, you still may be interested in this kind of arguments. Anyhow, now to the actual subject of my lectures. So I think maybe I'll put the notes somewhere for the time being, like here. So I think any discussion of, so this is about genera. So any discussion of genera, I think it's a good idea to start it with maybe the most classical example, just the Gauss map. What's the Gauss map? So if I have, suppose I have an orientable surface of some genus, and it's embedded, for now, maybe it's embedded in R3. So maybe call it C, anticipating the fact that it's going to be an algebraic curve. And then to every point of this curve, I have the normal, since it's smooth, I have a normal direction, and I have the tangent plane. And so using either of these data, I can move it to a sphere, namely have a point with oriental normal mapped to the sphere with the unique point in the sphere with exact same oriented normal. Right, so this is this Gauss map, maybe we'll denote it gamma. Okay. So if we were here, the sphere S2 will be maybe more canonically. What is the sphere? Sphere is the set of oriented lines in 3 space, so it's maybe Grassmannian oriented 1, 3 space, real. Or the same as oriented. So if I have an oriented line, then I have oriented perpendicular, so it's the oriented set of oriented planes, 2-dimensional planes in 3-dimensional space. So for every point here, we map to the corresponding point there. And if it's a map of surface to surface, then you can ask what's the degree of the map. So what's the degree of the map? If you look at any point here, you look at all of its pre-images and count them according to so there'll be some orientation. And if it's orientation, let's say they're all simple, then the orientation is preserved, you count +1. If the rotation is reversed, you count it -1, and that's called the degree of the map. And the basic fact of the degree of this Gauss map is 1 minus the genus. So this is where the word genus appears. So the genus, well, for the first time I write genus of C, not just genus. Okay? And so there are many, many, many different ways to prove it. And maybe one of them is if I draw my surface like this, and I look at the pre-images of the north and south pole. So it's like, if you look at the pre-images of the north and south pole on the surface, then of course they would be, so this would be the points on the surface where my tangent plane goes horizontal. So these are the critical points of this coordinate, maybe call it h, the height function. So these are the critical points, and then so this would be. And this critical points, this point will go to the north, this to the south, this to the north, this to the south, this to the north, and this to the south. And the orientation, whether the Gauss map preserves or reverses orientation, this has to do with the shape of the surface being either like this, or being a saddle. At the maximum or minimum, we get degree +1, and every saddle we get degree -1. So you get clearly, so there'll be, in this picture, it's clear that the degree would be 1 minus genus. But if the surface is embedded in any other way, that there's, again, the Morse theory will tell you that there may be more critical points, but since you can compute the cohomology of the surface using the critical points, the total number of those critical points, counting the index, would be 2 minus 2g. And since it's for north and south, so divide by 2, you get 1 minus g. Clear? So another proof is, so this is proof number 1. Another proof has to do with the fact that if I have, so if I have a vector field, so if I choose V, I choose V to be a vector field on the sphere. So it's a section of the tangent bundle, so section of the tangent bundle to the sphere. Then, so by the very construction, the tangent bundle here, so if I take the tangent bundle to my curve C, well, that's the pullback, right? Because you just have a space here, comes here, so the tangent bundle is the pullback of the tangent bundle to C. So if I pull back that vector field, it's a vector field on C. Sorry, C. Right? So if I have a vector field on the surface, I can count the sum over indices. So then I can take the index of this vector field V. Well, it's the sum over all points where this vector field vanish, the index of this vector field at that point. So if I have I'm on the surface. So if I have a point where the field vanishes, yeah. It's already almost in my mouth. I don't know. So is that better? Is that I don't know. So this is the vector field can as I go around the zero, the vector field can make some number of rotations. And so here it rotates with the circle. So this would be index 1. And in this picture, it will rotate. Sorry. Like that. And this picture rotates opposite. Maybe this is a little too long. So this will have -1. And in general, this is what? This is self-intersection. So this is self-intersection of my whatever surface with surface. I'll write say self. See inside the tangent bundle. So if I what are these numbers? So if I have a surface, it's something two-dimensional, tangent bundle something four-dimensional. So if I have a two-dimensional, I can self-intersect it, and this would be, and if I count with orientation, this would be plus, this would be minus. And so in any case, Hopf-Index theorem says this is also called the Euler class of the tangent bundle, and Hopf-Index theorem says this is the Euler characteristic of C, right? But since again now when we pull back something by a map, this depends on the notion of the index depends whether I go around this circle counterclockwise, clockwise or counterclockwise. And so then the fact would be the fact that the index of the pullback, so this would be, so then I can sum over all points. I can sum over all points where this original vector field vanishes. For each one of them, I get the degree of the map, because that's what controls the intersection, times the index at my original point. And so this would be just, so this is a common factor, it goes out, so the degree map times the index of V. And so we conclude that the Euler characteristic of the surface, which is 2 minus 2G, equals the degree of the Gauss map times the Euler characteristic of a sphere, which is 2. And so this is a baby computation with characteristic classes. There is for a vector bundle, there's something called characteristic classes that we define at some generality in a second. But so the characteristic, if the bundle is pulled back, then the characteristic classes are pulled back. And the Euler class is an example of characteristic class. It says, so if I have it says how many times a section vanishes with multiplicity. So take Euler class of a bundle tells you how many times a section vanishes with multiplicity. If I pull it back, then I get the Euler class there times the degree of the map. And you can write if you, so we're not gonna, so the topological computations we're doing today, they all have analytic counterpart. And the analytic, and we're not gonna stress on this, but this is what people very often see in applications. Because, so this is, if the bundle is pulled back by a map, then so you can pull back anything. We can pull back connection, we can pull back curvature, and so on and so forth. So on a sphere, so maybe application of that. So on a sphere, well, maybe it's too big. Well, I don't know. I drew it. Maybe I drew it too big. So the sphere itself, it's a homogeneous space. And in general, this will be very, very nice. We will always be pulling back for something which is homogeneous. So it's the rotation group divided by SO2. Okay. And you can use, there's an invariant metric on the sphere. You can, since it's a metric invariant under a group, then in particular, parallel translates with respect to this metric will just given by the action of the group. So you can if you want to translate along a geodesic, then you just act by an element of the group that takes you along that geodesic. And if I have a geodesic triangle, and if I see how much, so if I start with a tangent vector, let's have a tangent vector here, translated here goes something like that, translated there goes something like that, translated back it returns by some angle, maybe call it angle theta, and the computation of how much it's going to rotate will just amount to the commutator commutation in this group, and this theta is just equal in fact, so this theta is equal to the area of the triangle. So in particular, so if I pull it back, so I have a metric, I have a connection, I can pull back all that data there. I get some connection with the curvature which is pulled back. And so then I get the property that if I integrate over my curve C, I integrate. So curvature, usually people say curvature is a number, but in fact curvature is a two form. It tells you by how much you rotate as you go around a small parallelepiped. So if I integrate the curvature of the tangent bundle to C, well, this is what? This is an integral which is just 1 minus G times the same thing, since it's a pullback by this degree of this map S2. And here is the curvature here is just the area. And so this is, right, so you get the property that this is, so the area of the sphere. I sometimes have to remind myself what's the area of the sphere. It is 4 pi. And so you get the Gauss-Bonnet. So in principle, many integrals, and that's especially true in sort of modern high energy physics. They're written as Riemannian integrals, or maybe even infinite special integrals, but they have a meaning that they're characteristic classes of some vector bundles. So you can compute that integral by the rules of calculus, but you can also compute them topologically. And that's in some sense. So we're not gonna dwell on any kind of connections and curvatures. In many books, characteristic classes are defined in this way, but we're not gonna stress that point of view at all. And so, but in fact, you can do better. Instead of, so there are two analytic sides to this story. You can do better. Instead of just doing just integrals, you can talk about. So there's there's a somehow slightly different analytic side of the story. One relates to the integrals, and this is what I'm trying to illustrate in this example. And another has to do with indices of differential operators, or maybe more generally pseudo-differential operators. Again, some things defined analytically, but in the end, it's some essentially integer. And so there is that side of the story here too. And so what does it maybe I'll use this board for 1 second. What does it mean that the degree, so what does it mean that the degree of the map is this? It means, so if I consider the graph of the map, so consider, schematically, consider the graph of the map. So this is my S2, and this is my curve C, and there's some kind of map, kind of graph of this map. Now on the sphere, what I can do is I can choose a point and then stretch everything away from this point towards some other point. And so, for instance, on this, I can do like a Morse flow, make everything go from the north to the south. Right? So what would be the result of that? If I keep doing this, I will get the result where I have my graph becomes a subset where this part is just collapsed to this whole, maybe I'll draw, this whole blue part is collapsed to this point, and the rest are the spheres which are mapped with degree plus or minus 1, the total number with counting with orientation 1 minus g. And so in other words, I have my Gauss map, so this is to say that the Gauss map gamma, you can commute to a map that goes like this. From C, you go to a wedge of the spheres, and then here you just, so wedge means, if I contract, so what's a wedge of things? When I join things at a marked point, so I collapse all this blue thing to a point, I get a wedge of spheres, and then this each individual summand goes with degree plus or minus 1, and the total number is 1 minus g. Okay. So if you're computing a Riemannian integral, something pulled back from here, that's good enough because you're if you somehow, you're not really worried about a point because computing an integral, so this has measure 0, so whatever lives over that point doesn't matter. So you just for a Riemannian integral, this argument is fine. If you're computing indices of differential operators, that's not really good because this is not a smooth thing. But you can smoothly. So there's a way to write a smooth cobordism between the. So I'll just explain. So there's in fact a smooth way to interpolate the Gauss between the Gauss map and the union of n1 minus g spheres. And how does this go? So imagine I look at the graph of a function. So I consider a function of x, which is maybe x1 square plus x2 square minus x square. And so, and what does the graph look like? So the 0, f of 0, this is, well, I can't really, it's hard for me to draw this whole thing. I'll just draw it. So at 0, I get a cone, which I'll draw just like that. And then for means a quadratic function, so this is going to look something like that. So I'll just draw a graph. Something like so. And so if it's for positive t, it will go like that. for negative t, I'll go like so. I'm drawing the graph of this function. But since a graph of this function would require 4 dimensions, I'm skipping 1 dimension. So that says if I look at the f of f inverse of 1, this will look like, so if inverse is 1, maybe this looks like this. F inverse of minus 1, this looks like that. And f inverse of 0, this is a curve. Right? Everybody with me? So, which says that, so this means if I have a surface, I can in this way smoothly pinch any kind of handle on the surface, and in fact make a surface a bunch of spheres. In fact, they can make it nothing, because the surface in the 3 space is bound to 3 manifold, so you can it's cobordant to 0. But so the problem with just using this is an example of cobordism. This is some smooth manifold whose boundary, if I consider t to be between -1 and 1, the boundary is the value at -1 and the value at 1, and so that's a cobordism between this and that. The problem with just this particular cobordism in the context of the Gauss map is that it's not defined at the origin. At the Gauss map, at the origin, what's the Gauss map? The Gauss map here, the Gauss map of x, that is 1 over the norm of x times x1, x2 minus x3. And that's ill-defined at the origin, but we can fix it. We can put, subtract a small number times the norm of x, something like that. And so that will make what? This will make a hole, or make a picture like so. And maybe you think of a graph. What would the addition to this function do to the graph of a function? It will make a hole like that in the middle, and so this will lead to the fact that here I will get another sphere. And so now you see that smoothly, in fact, my Gauss map is cobordant really to cobordant. So this Gauss map is cobordant to the map you take the union, disjoint union of 1 minus g spheres. This means you take g minus 1 sphere and map it with the opposite orientation to the sphere. And so this is that makes sense? And so this makes sense that this has this kind of smooth interpolation. This has the advantage that it applies to indices of differential operators. So in particular, it says that if I compute the index, so of indices of elliptic operators in particular. So this is the sphere, the tangent bundle of the sphere has, you can give it a complex structure, and in particular, there'll be d-bar operator. So you can study the index of d-bar operator going from what? You're going from the functions to functions valued in anti-holomorphic forms. I write like dz. Okay. It's an elliptic operator. And so this would be, so this says the index of this operator so the index of this operator for the curve C, this would be 1 minus g times the index of this operator for S2. And so what is this index of this operator? That's the same. So you have an elliptic operator, it will have some solutions, some kernel with holomorphic functions, some co-kernel, which are this you can, so in this case, co-kernel, in fact, co-kernel, this function is really, so the kernel of this d bar, this is, if I, these are holomorphic functions. One co-kernel of this d bar operator, that has to do with holomorphic differentials. And so that says not only this, some kind of Riemannian statements are, or you can compute topologically, but you can compute statements about indices of elliptic operators in this topological fashion. And so in these lectures, we will not deal with Riemannian integrals, and we will not deal with elliptic differential operators. Instead, when we see this, we say, well, that's just the Euler characteristic of the sheaf of holomorphic functions. So this is the, why is that? Is because if I take the sheaf of holomorphic functions, that this is the kernel. It's a, so C infinity functions. This is d bar. Z goes to 0. As a sheaf, this is surjective here with the kernel here. And so if you're computing the index of this operator, you might as well compute the usual Euler characteristic of the sheaf of holomorphic functions. And this you can tensor. This you can tensor with any holomorphic bundle you want. And then this will compute the Euler characteristic of the sheaf of sections of this holomorphic bundle, the index of that operator. Z bar, yes. So we will not be, like I said, we will just in all situations when we have actual computations, we will have the manifold will be complex. This will be a sheaf of holomorphic functions, or sheaf of holomorphic sections of some vector bundle. This is a sheaf and it has a usual Euler characteristic, namely the alternating sum of its sheaf cohomology. And this is, we'll just compute that. But in principle, it computes, you can also phrase it as an index of a differential operator. And the hardest thing about this differential operator is to remember how to spell its name. I believe it's called like that, but it's maybe the hardest notion here. So okay, so now maybe to summarize to summarize this discussion, there's ways to they're interesting. Maybe what we're supposed to take from this discussion. There is very important notion in topology, the notion of a vector bundle. We'll get back to that in a second. This vector bundles, with vector bundles, you can associate, in particular, if you have a manifold that has a manifold by definition has a tangent bundle, very important bundle. And to bundle in general, in particular to the tangent bundle, you can associate characteristic classes, which are either they have to do with connections, or either have this cohomological flavor, and they have to do with connections, curvature, and so forth, but in the end can be computed purely topologically. Or you can maybe slightly more refined things that have to do with elliptic differential operators, and so forth, but in the end also can be computed topologically, just with a little more sophistication in topology. And this is the Krichever genus in elliptic thing. So so there's cohomology, there's something called K-theory, which we'll discuss in a second, and there's something called elliptic cohomology. And Krichever genus is some elliptic function you associate to to a bundle on a manifold. And that again has some features, and which will be the subject of this lecture. Okay, so now. Right. So now a little bit more systematically. So suppose I have a tuple. Suppose X is as a nice topological space, some compact Hausdorff space. So this is so I'm not trained in general topology. I'm gonna stress any kind of general topology notions. All topological spaces we'll see in this lectures, they're all simplicial complexes or smooth manifolds or something like that. So this is, and so then, so this is, you associate to this a certain group, the K group of vector bundles, and what's a vector bundle? So to this you associate K of X, or also known as K0 of X. This is a ring. What's an element in this ring? So this is so first of all, what's a vector bundle? A vector bundle is also a topological space which projects to X, and the fibers are vector spaces. And so they will be interested in complex vector spaces because this is this is more interesting. So there's the notions of complex vector spaces. And the bundle is called, and we only consider locally trivial bundle. This means that if I look at the neighborhood of each point, there's some open neighborhood such that over this neighborhood, so a bundle may be called the bundle. So the total space of a bundle is called E. There is a map projection to X. And so if I look at the pre-image of this neighborhood U, this will have to be a product. And the transition functions, they're all transition. If I want to transition functions between different neighborhoods, they will have to be linear function in the fiber C. That makes sense? So such things, so if I have, maybe I should call this bundle V. My bundles will be typically called V. So if I have such object that I can consider, so given two bundles, I can do the following. I can form their direct sums. It's another bundle. Because this has to do with the fact that my transition functions lie in the group GLN. And so this has to do with the fact that if I have the group GLN1 cross GLN2, I can map it to the group GLN1 plus N2 and make transition function for a bundle just by stacking the matrices together. And this will be transition functions for a new bundle. And then I can also form a tensor product, which has to do with the fact that if I have, and this just corresponds to the fact that I can take, what this map? This is the maps of automorphisms of one vector space times automorphism of another vector space going to bigger vector space. That just corresponds to direct. So inside here, so maybe I should say. So when X is a point, then bundle is just a vector space. And so if I have some operation for a point, which is to say I can stack the vector space that forms direct sum, then I can, using the same operation, I can make it for a vector bundle and have the tensor product, similar for the tensor product of vector spaces. And these two operations, these two things make the set of isomorphism. The set of isomorphisms. Classes of vector bundles into a semi-ring. Semi-ring means where you can add and you can multiply, and this is distributive with respect to one another, but you cannot subtract. But you can introduce subtraction formally. So if I have formally, so define K of X. This is semi-ring. There's the semi-ring here. With subtraction formally added. So what does it mean added? It means just I can start with just an element be a sequence of, I can choose V1 minus V2, just a symbol. And I say, well, this is isomorphic. I equate this to some maybe W1 minus W2. Well, what does it mean they're equal? Well, that means that, so this means V1 plus V2, well, is actually equal to W1 plus V2. That makes sense? Then, what? Right. I mean, we didn't introduce any other key, so this is for now KZ. And then you observe it's kind of a really basic fact and will be very, very important. Is that for any bundle, V, there exists an embedding into a trivial bundle. So, or put it differently, you can say any bundle V is a quotient of a trivial bundle. And this is maybe quotient is easier to explain. Is that, well, if I have a section is a map from the trivial bundle, a section of a bundle is a map from a trivial bundle to your bundle. And so if I have enough sections, if I have finitely many sections, which is assumed where the compactness is important, with finitely many sections, I can generate my whole bundle. So there'll be surjections or equivalently. We'll see this equivalently. There's a surjection from the trivial bundle. Easier. So if I have surjection, then going to the dual bundles, you can. The bundles also have dual bundles, and so if I have a surjection from trivial to your thing is the same as embedding for the dual bundle. So, and this is just find enough sections, and you can always, using partitions of unity, you can always find enough sections for any bundle. So this is, but then we're not doing algebraic geometry here. We're doing topology. In topology, so in algebraic geometry, things get really complicated. But in topology, things are very straightforward. If I have a quotient of a trivial bundle or sub-bundle of a trivial bundle, I can just take the perp using any metric I want on the bundle. So I'm not doing algebraic geometry, I'm just actual topological space of a sub-bundle. Then I can take the perp of that sub-bundle and have a bundle which is complementary. In other words, I have for any bundle, for any bundle B, I can write in the form. There exists any bundle A, there exists some number n, sufficiently large, such that V direct sum, the perp of V inside here, well, it's just a trivial bundle. So it's enough in this, when I want to subtract something, I might as well subtract. So I might as well assume that these are trivial, can be assumed to be trivial. Because if I, so this is to say that minus V equals minus Cn plus V perp. If I want to subtract, I might as well subtract the trivial bundle. And so in particular, in this relation, the relation that you identify, the bundles are equal in K-theory if they're stable isomorphic. Means you add a trivial bundle and they become isomorphic. It's a non-trivial relation. Like for instance, we're doing complex K-theory, but in real K-theory, if I take the tangent bundle of a sphere and add a trivial bundle, then this is trivial because the normal bundle to the sphere is trivial. The sphere is orientable. So if I take the tangent bundle plus the trivial bundle, I get the ambient R3 restricted to my sphere, so it's a trivial bundle. So this is a non-trivial relation. So two bundles are the same in K-theory if they become the same after adding some trivial bundles. So but more importantly, yeah, I guess you took my water. Is there some other bottle of water there somewhere in that? Oh. Yeah. So more importantly, in this construction lets you define analog. Remember we had this Gauss map. And this construction gives you an analog of the Gauss map. Namely, you say that, so if I have some bundle, so this is my space X, and I have some bundle V. So maybe I'll first draw a trivial bundle of some rank. And then I have my subbundle V, which is subbundle in the trivial bundle. Then I get a map to where? I get a map from at every point of X. This is just like the Gauss map. At every point of X, I can record which subspace in this fixed Cn corresponds to V. So I get the map to the Grassmannian of rank V-dimensional subspaces inside an n-dimensional space, the complex Grassmannian. Clear? And moreover, over this space, there is a tautological bundle. Whose fiber over a point. So what does correspond? this parameterizes, this thing parameterizes various, so inside of my Cn, this parameterizes subspaces of a given dimension. And so in particular, there is a bundle over that whose fiber is the space itself. Okay. That makes sense? And this is, so this is, maybe I'll write it as before it was a Gauss map. And my bundle V is the pullback. Sorry, is the pullback of this topological bundle. So we have all of the structures, all of the kind of structures that we had in this example of the Gauss map before, we can kind of develop in this situation. This Grassmannian is a very, very nice manifold. And it's a homogeneous space and so on and so forth, has a lot of geometry. And we can, all of that we can transplant here. Or equivalently, we can think of trying to take, in some sense, what we would like to do is understand something about like a push forward of X under this map. In some cohomology, in homologic Bordism or something like that. This is equivalently, either we're trying to pull back some data here and integrate over X, compute integrals or compute Euler characteristic, or we can try to say where this X itself pushes forward under this map. That makes sense? So why it's much better to take complex coefficients? It's because this Grassmannian, this cohomology, is much more interesting for complex Grassmannian. For real Grassmannian, you can study the cohomology of the real Grassmannian. This is also interesting, but it's all it's all Z mod 2 torsion, so it's not super interesting. For the complex Grassmannian, it's much more interesting. And moreover, since we're interested in things which are stably the same, so this is, we can think of what is supposed to happen is I'm free to increase n. I'm free to add trivial bundles to that. So I should really take a limit. So maybe we'll denote this rank by R. I should really think of a limit. So it means take a union over all. So take a union over all n of Grassmannian R n. See? So union of all the Grassmannians, increasing union of them. And this has the property that, in fact, the cohomology under this embedding, the cohomology extends very, very nicely. And so this Grassmannian, so you can say, if I embed, in other words, if I embed the Grassmannian inside the bigger Grassmannian, then the cohomology surjects. So this is so the map on the cohomology is surjective. And so the theory of characteristic classes so in cohomology, this is about the pullback under this map of the cohomology of this infinite Grassmannian, right? Grassmannian R infinity. And what is this cohomology? What does it look like? So let's start with R equals 1. And the Grassmannian of one dimensional. So this will be about character. So R is the rank. So so for R equal 1, it's about bundles of dimension 1 called line bundles. So this is Grassmannian for one-dimensional subspace inside n-dimensional space, and I drop C, that is the, just by definition, the projective space. And I'll also drop C here, so the projective space of dimension n-1. And this has a very nice cell decomposition. Composition, which you can, if you have never seen it, then you know, just one of the problems to do it. And again, the beauty of the complex case is that all the cells are complex cells. So there's all of even dimensions. There's no boundary maps between them. And so in the result, the cohomology of the projective space, this is generated by the class. So this is projective space. It has a space of dimension, open cell of dimension Cn minus 1, and has a complement, which is kind of the points at infinity. So this looks at the minus as a one-dimensional smaller projective space. So this is something of codimension 2, and it's point. So this is in terms of algebraic geometry, that's a hyperplane. You equate one of the linear coordinates. So there's the class Poincare dual to this hyperplane. So it's a codimension 2 class. It's this Poincare dual class. Maybe I'll denote it X. And then and that satisfies the relation. Well, if I intersect, so if I intersect X, if I intersect 2 hyperplanes, I get a linear space of codimension 2. If I intersect 3 hyperplanes, I get a linear space of codimension 3. And at some point, I run out of dimensions, so x to the n equals 0. So x to the, have my capital N and small n confused. So as n increases, so if n increases, that just becomes polynomials in Monday. If I take n larger and larger, I mod out by higher and higher powers of n, and in the end it's just this. And so what? Well, you're right. It depends on what you. Okay, you can. So with all these things, you always. Yeah, okay. It depends how you mean. Right. You can take it. This is always the case whether you take. You know, this is like maybe when you open McDonald's book on symmetric function. In some sense, it's all about symmetric functions. The theory of characteristics of McDonald's book symmetric function. One of the first pages, it says. And when you define symmetric function, you take the inverse limit and the category of graded algebras, which means you only allow things of bounded degree. So that here you can, when you take a homology of such space, you can also consider where you take the inverse limit or inverse limit in the category of graded algebras. So you don't object to the series. Is it serious? I don't know. It doesn't subtract or add anything, so we can take series. No, I don't object. I mean, it's fine. It's a good thing. So okay. So then what? So then we take right. So what's another point of view on this? So this infinite projective space, which is after all the union. So one way to write it, it's the infinite linear space, which is just means the union of all finite dimensional spaces. And then you take out the origin, and you mod out by GL1. Right? Or equivalently, you can say This is infinite dimensional sphere where you mod out by u1. You take a vector of length 1. And so this object, infinite dimensional space or infinite dimensional sphere, is in fact contractible. So and so this is a contractible space on which the group acts freely and you mod out by the group. So this is by definition called as classifying space. And denote BU1. Right? What does it? It's just why it's called classifying space. By this construction, every bundle, every line bundle is, classified by a map to here. So which is called why it's so a map. A line bundle is the same. So in general, so this is already in Pasha's lectures. If you have a vector bundle, it means you have some transition functions. It's equivalent to the corresponding principal group bundle. So a vector bundle of rank n is the same as principal GLN bundle. So or principal UN bundle. And so that's the line bundles are the same as principal U1 bundles, and they're classified by a map to this, and this is called classifying space. Now, in general, similarly, this Grassmannian R infinity, this is similarly, if you think about this like that, this is you take matrices. What's a Grassmannian? You take maybe first Grassmannian n. Grassmannian size n. What's that? So how can I parameterize an n-dimensional subspace? I can think of a map from an r-dimensional, so this is I look at the space of homomorphisms from an r-dimensional space into n-dimensional space. So I parameterize my subspace by coordinatized by choosing a basis in it. I look at the locus of maximal rank, and I mod out by GLR acting on the source. This is the fact that you take some open set and you mod out by the group. That's also expressed in algebraic geometry. It's a GIT quotient. This is stable locus, and you express it like so. In other words, this is the space of R, by n matrices of rank R, and then you mod out by GLR. And so then, of course, if you'd want this to make Grassmannian R infinity, well, it's the same thing, except you make this matrices infinite. And so if I look at the space of infinite matrices of rank R, that is a contractible space for the same reason as this space was contractible. And so this space, this Grassmannian, it's BUR. And so it classifies UR bundles, well, again, through this construction. And now, very generally, if you have just from general principle, if you have a homomorphisms of groups, this always induces a map between the classifying spaces. The same direction. And so what is this? To use this here, we're going to use the maximal torus, which is maybe I'll write it u1 to the power r, mapping to UR. Take a maximal torus inside this group and go here. So this should give me a map from BU1 to the power R to BUR. And what is this map? The map is just what is this map? It just splits this matrix into columns. So if I have finitely many vectors, I put them together, this may not have the maximal rank. There will be some locus where these vectors are linearly dependent. But I have an R tuple of non-zero vectors of infinite length. Then the locus where they're linearly dependent, that's infinite codimension. So this is, if I take, so this is to say there is a well-defined map like that. Because things, if I take, R tuple of non-zero like vectors of infinite dimension, add them up, then this is up to infinite codimension. That's a well-defined map, and this induces a map in cohomology. And so this says to say that the cohomology. This says that the cohomology of this BUR, this maps inside the cohomology of that space, which is the polynomials in our variables. And in fact, what is the image of this map? The fact it maps it isomorphically into the image, which is just symmetric polynomials. Because again, it's sort of like in Pasha's lecture when he was taking a G bundle, reducing to the maximal torus, and this is to say if I have a subspace, I can choose to write, if I have a bundle, I can choose to write it as a sum of line bundles, but that's up to an order. And so there is this symmetrization there. And so then the Chern classes abstractly correspond so abstractly the characteristic classes correspond to I have for any symmetric polynomial, I want bundles of rank R, its characteristic classes, I take any symmetric polynomial, and that defines me some class in cohomology. So this is a class in cohomology where the degree of each variable is 2. Yeah. Make sense? So again, if you open McDonald's book, then you see that this is this algebra of symmetric polynomials is freely generated by elementary symmetric functions. These are symmetric functions. Elementary. And these are called corresponding. These are called Chern classes. What's the geometric meaning of Chern classes? The geometric meaning of Chern classes. So the meaning have geometric meaning, and then the following. That this is maybe first let's talk about let's talk about the top Chern class. So CR, which is, if I don't want to always remember where the what's the rank of the bundle, I will sometimes write C top. This is a class. This is a cohomology class of dimension 2R. So real defines some condition of codimension. So this is 2R is the real dimension. This is the real dimension of CR. And this is the locus where a section vanishes. Of, strictly speaking, the dual vanishes. So this is the dual, well, in real topology, in real topology, there is really no much difference between the dual space. I mean, up to orientation, up to constant conjugation is the same, but on algebraic geometry you can do this. So if I have a manifold of a bundle of some rank, I look at the section, generic section. This would be our equation. So it's something of defines me as something of codimension of complex codimension R, real codimension 2R. So it makes sense that this is a class in this cohomology. And how do we see this? Well, so this is all right. And I said, so to say what's the in my previous notation, that is supposed to be ER, and this is supposed to be the R symmetric function of x1 to xr. This is just product of n var x to xr. Right? And what if I look here, what does it mean the section vanishes? So if I look at this picture here, so this any kind of statement like this, it's enough. So every bundle, so this is again the same principle at work. Every bundle is pulled back from the universal bundle. So it's enough to prove the statement for the universal bundle. What does it mean for universal bundle? For universal bundle, how do I get sections of the universal bundle? I have homomorphism from, so this is this quotient, this becomes the tautological bundle. So I have a homomorphism from the tautological bundle to the trivial bundle. So if I take any linear function here, I get a linear function on the tautological bundle. So I get a section of the dual tautological bundle. So what does it mean to take a linear function here? It means take any row of this matrix. If I take a row of this matrix, means I apply a linear function to this here. So I pick a row, and I want this row to vanish. What does it mean for row to vanish? Row to vanish, so remember we had our basis vectors, and we need all of them to have one coordinate vanish. Right? So this is a bunch of basis vectors. For each of them, one of them, there has to be the first coordinate, or any fifth coordinate has to vanish. That is a hyperplane condition on each of these basis vectors. So this is what it's. So this means each of these basis vectors has to lie in this hyperplane. So this is what this condition said. Right? That clear? So more generally, well, the fact that this is invariant, this is kind of clear because this map is equivalent with respect to permutation. That the fact that it has the line invariance, it's clear. The fact that it actually maps isomorphical to invariance, maybe you need to argue a little bit. Because here you just take a tuple of vectors and stack them together. It's obviously symmetric. Right? So this is whatever you're going to get as a pullback under this map have to be symmetric. You it's a little argument to prove that in fact this. All right. So now more generally, I claim that if I take C R minus I, this is the locus where maybe I have to look at my notes for this to get the indices right. So this is, I believe, this is where I minus, so I plus 1, right? Where I plus 1 sections are linearly zero. And this, how do we, this statement, in fact, immediately reduces to this statement by the following kind of reasoning. That this is supposed to be some general statement about all bundles, right? So somehow this is for all possible bundles is the statement. And so then, in particular, it has to be the case when, in particular, we can take V to be of the form a trivial bundle of rank I plus some other bundle. And so a trivial bundle, from a trivial bundle of rank I, we can certainly make I basis vectors, and then not just a basis, and then one more, and then nowhere vanishing, nothing. And so you only get, so this for bundles like this locus is the same as where the section of this bundle vanishes. So this locus, so this dependence condition is the locus where this section of this bundle. In other words, if I write a matrix, 1, 1, 1, 1, and then I ask for something, one more. So maybe I'll write it like that. So if I ask matrix 1, 1, 1, 1, and then something, and then it doesn't matter what here is. What's here doesn't matter. So when does this matrix drops rank? This matrix drops rank exactly where this vector is 0. And then the elementary symmetric functions have the property. So this is again. Yeah. Yeah, this is a locus. This is codimension. The complex codimension is R minus I. And this is somehow the codimensions work out correctly. And the elementary symmetric functions have the property that the metric symmetric function has the property that it's its unique symmetric function of a given degree. So maybe I'll ask for, say, E maybe E3 is the unique of x1, x2, x3, and so forth. This is the unique symmetric. This is maybe problem number 1 on the homework or something. This is the unique symmetric function of degree 3, such that if I leave 3 variables and pad everything by 0, then I get x1, x2, x3. It's a simple thing. It's an exercise. So that says the Chern classes of a trivial bundle are trivial. And so this padding by zeros corresponds to adding a trivial summand. And so then it means if you add something sufficiently trivial, ask for this kind of condition, you get the Euler class. Make sense? Now I have to see what else I was trying to say, right? And so okay, maybe to reiterate. But that was a good board. So maybe we can agree. So maybe I'll say it one more time. So if I have so what is again characteristic classes? So characteristic classes in cohomology so if I have characteristic classes associate a bundle V on some topological space X, and bundles will be always complex. In cohomology, this gives me this kind of Chern classes, C classes C, K, or V, which are the some kind of classifying maps gamma pullback of the corresponding EK. EK is in cohomology of Grassmann. And then I can, for instance, I can multiply these classes so that they add to the dimension of my manifold, and I can integrate over X. So for instance, in our situation with the Gauss map, there was a bundle of rank 1. It had first Chern class C1, which is the Euler class by this board. And so we were just looking at the Euler class. So the Euler class had degree in a computer. That's had to do with the degree of the Gauss map. So in K theory, you'd think that this is, maybe you should similarly study, well, what do you think you should do in K theory? In K theory, you think you should maybe similarly, study like K theory of that space and so forth. But in fact, that's unnecessary. K theory is in some sense like the best. In some sense, K theory is maybe the most concrete, in some sense, in my view, maybe the easiest of all cohomology theories. All you do is the analog of that is just the fact that you can take tensor operations of your bundle B. So with the bundle B, you have also tensor operations. So every tensor operation, you can have some tensor product of various exterior powers for bundle B. So this is the exterior. So you can have cup product. So this is some sort of analog of you take the cup product of CKI. And so while in cohomology, maybe you integrate over X the product of this CKI of V. These are some numbers you're going to get. Maybe in K theory, you compute the Euler characteristic of this bundles. So I have maybe a few minutes left. I don't feel like starting a new theme, but maybe I'll say a few words about where this is gonna go in the future. So in general, a cohomology theory is a contravariant functor from spaces to something, to some rings or abelian groups or something. That is to say, you have if maps, if spaces map one way, then cohomology, they pull back on their map, they go the other way. And so, but to get interesting numbers out of topological computations, you're going the wrong way. You're trying to push forward. So this operations of integrating something along X or computing the Euler characteristic, they're examples of push forward in this theory. So that you have to define push forward is not abstractly defined. You have to define what it means to have a push forward, and we'll talk about that in due course. But this going the other way, this gives you interesting numbers. You not get so if you want to get a number, so you have number, so you have all topological spaces, and all topological spaces there is point. Of course, you can pick a point and map to the space and pull back something via this map. You're not going to be something very, very interesting. But if you go the other way, if you have a map to the topological space and map it to the point, then you have some notion of push forward under this map. That gives you some interesting global thing like that. And that, in this situation, it's a number, but in the situation when we're going to consider, there will be a group action. So there will be some group, some compact group G acting on X, and will also act compatibly on this bundle. In which case, these numbers will be not numbers, will be functions on a group. So this is how you get interesting functions from topology. You start with a wrong way map. You start with a wrong way map in push forward map in equivariant K-theory, equivariant cohomology, equivariant elliptic cohomology, and you end up with a function on a group. And then this is an interesting function. And so this is in this case it will be an actual. So if I have a group acting on the so this would be in the case of K theory, this will be a representation. This will be for me the virtual representation. Of a group G. And so the trace in this representation would be a function on the group. And this would be a function on, this would be like a differential of that function, be a function in Lie algebra. And in elliptic cohomology, where this Krichever words belong, this would be a function like an elliptic function on the group. And the basic result about it is Krichever's theorem is a certain rigidity theorem. And what does that rigidity theorem says is that, well, there's in the end, it's like a Liouville theorem. There is no, if you want an actual elliptic function, then there's none, right? If you want actual non-singular elliptic function, there's none such. And so in some sense, this theorem is not particularly, the rigidity theorem is not particularly surprising if you can define that number topologically, because if you can define this number topological, that says you're going to get like an elliptic function in the group, and okay, there's no elliptic functions, and so this would be a constant. Anyway, so that's. I think I have 1 minute left, but it's I think it's okay to end with it.
Okay, thank you. So we have 1 minute for questions. Any questions?
Right. So this, what was it for the? It's enough to prove it for universal bundle. For universal bundle, what is it? You have, you look at kind of infinite by R matrices, and what's in your row of this matrix is a section of the dual bundle. So if the row of this matrix is 0, that means this was an R tuple of vectors, means for every one of them, the first or whatever, first coordinate is 0. But the locus where the first coordinate is 0 for each vector, that's a hyperplane class. That's the corresponding x. So x1 is where for the first vector the first coordinate is 0, x2 is for the second vector the first coordinate is 0, and so forth. So that locus is really the product of hyperplane conditions. So that is x1, x2, x0. Yeah. Yeah. No. Any section. So this is. It's clear that it's rather clear that this is. If I take any section, any collection of section, that would be you can have any collection of section, any other collection of section. You can interpolate between them, and so that will be certainly define the same cohomology class. Yeah.
The formulas are mapped from X to this one, from the line bundles. It's always from X to the point.
Say it again. Here? Well, point modulo group or something like that. Yeah. In that sense, it's a map to the stack if you want. Say it again. No. Here it's C had to do. I had a complex vector bundle. So it's a map to n-dimensional, r-dimensional subspaces of that fiber. Yeah. So it's just my fiber is C to the n, and this C to the n is this C. Yeah.
Okay, I think let's go for the coffee break because remember we have discussion exercise sessions.
Right.
Perfect opportunity to ask these questions.
Everybody knows that the problems are posted online. Yeah. Right? Okay, cool.
To be collected and graded by.
Yeah, exactly. Yeah. So if there's no grade, but if you want to actively participate, it's encouraged.